Welcome! The subject of this video is using Pnp transistor switches with microcontrollers such as Arduino, PIC, and etc. I'm your host, Louis Laughlin. Visit my website at www.bristolwatch.com for lots more electronic projects and gadgets. Let's get started. First of all, let's take a look at an Arduino's electrical connections. Note first that it has a negative common and a positive VCC of 5 volts. If you exceed 5 volts on Arduino at any point, you will destroy the device. Also note that its I/O pins can source or sink, that is, put out or switch to ground, no more than 20 milliamps. That's the limit. Again, note this: an I/O max of 20 milliamps and a common negative. A quick note on PN junctions, that is positive negative semiconductor junctions, particularly silicon, which is what we will be dealing with extensively. When forward biased, that is, the anode is positive and the cathode is negative, it will conduct a current, and you will have a voltage drop from between 0.5 to 0.7 volts. If you connect the negative to the anode and the positive to the cathode, it will be open. There will be no conduction. It's like somebody opened the switch. Bipolar transistors come in two main types, NPN and PNP. In the case of a PNP, which is our subject here, like the NPN, it's a 3-pin device, but the electrical polarity is opposite. Mostly we're going to be using this in the common emitter configuration. That is, you need a voltage, a negative voltage on the base with respect to the emitter. This will produce a current when it forward biases the NP junction. The amount of current flowing through the base to emitter or emitter to base, either way you want to look at it, is multiplied by HFE to give me an emitter to collector current. Also note briefly that these transistors come in a number of styles, from surface mount to large metal cans such as a TO3. Just because it looks like this doesn't mean it has a transistor in it or any particular type. It could even be an SCR or a triac. Check your spec sheets. Briefly, let's look at the circuits we have here. We have a switch, we have a light emitting diode, the current limiting resistor, and VCC. Note that in both of these circuits I have a common negative and a positive VCC. In all of these videos, current flows from negative to positive. So when I close the switch here, I have current that moves up from ground through the switch, through the LED, the resistor, up to VCC. It works the same for either side, but you notice something, that the switches are placed in different location. The switch in this case on the left is placed in the sink configuration. That is, it is placed in the ground side of the circuit. Over on the right, you notice that the switch is connected in the VCC side of the circuit. This is called source because the switch switches on and off the source. On the left, we call this sink because when the switch is connected, the current moves through the ground up through the switch to the load. This is important to note, these principles here, because that determines how your transistor switch will connect in the circuit. Again, note, if the switch is in the ground side, it's a sink. If it is in the high side or VCC, it is a source connection. Alright, looking here These, if you're using a negative ground, which you're stuck with Arduino, PIC or any other modern microcontroller, they use a negative ground and a positive VCC. So you will have to connect the commons of the two together. But because of the output being plus 5 volts or plus 3 volts, you have to handle the transistor drivers differently. The Pnp will only operate to a large degree in the source configuration. You notice here's VCC, here's my transistor switch, here's my motor. I press the switch, I have current flow through the resistor IB, producing a current IB through the base emitter of the Pnp transistor, which switches on the collector emitter junction. Thus I got a current flow and my motor runs. Look over here on the other side. The emitter is connected to ground. I connect this switch, I get a current from ground through the emitter base, through R2, through the switch, back to VCC. That will, of course, produce 0.6 volts on the base, which tells me it's forward biased. And of course, I have a current IC that cuts on my motor. Note up here that while the emitter on the Pnp is 12 volts, the base is 11.4. If I was to connect the negative meter lead to the positive up here and then connect the positive lead to the base, I would read negative 0.6 volts. That means it's turned on. It has to be negative 6 in respect to the emitter. Okay, another way of saying it's less positive than the emitter is the same thing. Now let's connect the a Pnp up as if it was in the sync configuration like we would a NPN transistor. Of course, I'm going to have to reverse my battery. The positive's going to go to ground. The negative has got to go, and I also have to turn my LED around. Note, if I didn't mention it before, the arrow points to the negative material in the LED. That's not current flow. You should have seen this if you'd already seen my video on NPNs. But nonetheless, this will never work no matter which way I turn the battery. Because if I have a high out of Arduino, well, it's going to be 5 volts. I'm putting plus 5 on an N-type material, Pnp. It's positive with respect to the emitter and thus is turned off, and it will never work. Arduino cannot put out a negative 5 volts. Won't work. Here is the proper way to use a Pnp driver transistor. Okay, it looks a little more complicated than you thought, and I'll explain why. Here is Q1. It's going to be a TIP42. It's rated at 6 amps and has a HFE of 20. HFE is beta or DC current gain. Q2 down here is an NPN transistor. It's a 2N2222, has a 1 amp collector current and an HFE of 100. When transistors are connected in this manner, this is sort of, I call it an inverted Darlington in a way. But nonetheless, whatever base current comes in on Q2 here from Arduino, it's going to be multiplied by 100 HFE, and that's going to give me an emitter collector current that's going to move through the base emitter of Q1. So let's look at it this way. What happens is the HFEs of the two individual transistors multiply together. So the HFE of Q1 times Q2 is 2000. I have a motor here that I need 3 amps. So how much current do I need to draw from the Arduino I/O to give me 3 amps? Well, the IB of Q1, that's 3 divided by 20, is going to need 150 milliamps. I'm going to need 150 milliamps through Q2, through RC, through the base, back to VCC. Okay, well, there's another way you could look at this. Since both of these together is 2,000, divide 3 by 2,000 and you get 1.5 milliamps. That's very small. And so Arduino would only need to supply about 1.5 milliamps to Q2 to give me 3 amps out of Q1. Okay, so if you look at it this way, subtract 0.6 volts from 5 volts, that leaves me 4.4 volts. Divide that by RB, that's IB, that's your base current. Okay, divide by 1.5 milliamps, it says 2.9K. I would use a 2.2K. You always want to use a smaller one because I want this switched on. What that means, it would be the same thing if I had that switch connected into the base. I want Q2 to do the same thing that this switch here does back in this circuit. That's what I'm using Q2 for. Go back here, and when Q2 is fully switched on, it will have a 0.5 volt on the collector. It'll be that should be 11.4, not 11.6. Nonetheless, I will get the current flowing through here just like I pushed the switch. If I want to know the value of RC, well, I got to get 150 milliamps through there. Well, to do some, let's see, divide 10.9 by 150 milliamps, and you can figure it out. It's not that important. It's probably about 1K. No, it's probably about 400 ohms. I didn't bother doing it here, but I hope you get the idea. To reiterate, okay, the way this circuit works is I have to get 150 milliamps through the base emitter base junction of Q1. I'm going to use this instead of a push button switch. I'm going to use this 2N2222 acting as a transistor switch. Okay, Q1 is set up in the source configuration, but in regards to Q1's base, Q2 is set up in the sink configuration because it's in the ground side of RC. So I only need about 1.5, 2 milliamps in the from Arduino through the emitter base circuit of Q2 to fully switch on Q1 and give me 3 amps. Okay, finally, why did I have to use Q2? Because if I connected this 11.4 volts through a resistor back directly to Arduino, that would exceed 5 volts and blow the I/O pin. So Q2 is protecting Arduino from the 11.4 volts up here. Here is another variation. We have an MJ2955. It's rated at 20 amps. We have the TIP42. It's rated at 6 amps. Each have an HFE, that's a DC gain of 20. And then again, I have a 2N2222. Alright. This is called a Darlington configuration, which we'll go into in another video. Nonetheless, what's going to happen here is we're going to have the current move through the emitter base here. We're going to have a current flow. When I switch on Q3, I'm going to have a current flow emitter to collector through this resistor, it's going to go into the base emitter junction of Q2, which is going to multiply that current by 20, and then it's going to, and when it goes through the base emitter junction of Q1, it's going to be multiplied again. So if we took the HFE of 20 times 20 times 100, it's 40,000. Now, I'm not going to magically invent infinite current here. The current is limited by the motor, but I want this switched on. I want it switched on hard, and I want my 10 amps for my motor. As far as IB goes, use with an Arduino, use about 2.2K. I don't even bother to calculate these. They're so easy to use. You will have to watch the value of IC. You're going to have to drop about 10 volts. Okay, let's do this. What's 10 amps divided by 40? Well, 400. It's a small amount. This is probably about 330 ohms. This over here is about 2.2K. Should get you running. Should cut your motor all the way on. Here is another variation of the previous circuit, except we're using an MJ 908 amp. It is instead of two separate transistors, it has a single transistor built into the same case. It will look, you won't know it's a Darlington unless you look up the number. Okay, I got a 5 amp motor. That's well within the 8 amps. Okay, this here has a gain of 1,000. Well, 5 amps divided by 1,000 is 5 milliamps. I just need 5 milliamps through here. 10.8 volts divided by about 560 ohms for R1. 2.2K for R2. You can be approximate on these. They're not that critical. Okay, so that's an introduction to Pnp transistor switches. Of course, I went into much more detail on the NPN transistors, but the ideas are exactly the same. You have to pay attention to your betas, which is HFE, your collector current max, and be wary of how you hook this up. Once again, the Q1 up here is in the source configuration, Q2 is in the sink configuration. All of this will make a lot more sense as we move through this series and look at H-bridge motor controls. And we'll also be looking at MOSFET switching circuits. Until then, this is your host, Louis Laughlin. Thanks for viewing the video.